and back to rotating turbulence. Say the motivation of the atmosphere and the ocean, but staying in the framework where we are not trying to be realistic, but except for one thing, which is the Valence number. Okay, so it's work done with Pablo Minini and Joel Mortenberg. So the question is, return to isotropy, and we have two reviewers of our paper. One says, of course, I mean, it's obvious, and the other one says, but it's well known that it doesn't happen. And the devil is in the detail, which is, what are the parameters? In particular, do you resolve the scale, or you expect that isotropy is being recovered? So this is a picture stolen from Bodenschatz, because it's a nice picture, saying that there is plenty of turbulence, even if people at Helicarp don't always believe it, but all from the micro scale, from fragmentation and coagulation of clouds all the way to planetary scales. Okay, so I talk about turbulence and waves. That's not very original, and here the waves are due to rotation. It's going to be solid body rotation. And helicity being the sugar on the cake. The question will be, is there a return to isotropy in the small scale? And I'll finish with some questions. So I didn't bother to write the equations. I think you know them in this audience. I remind you that helicity is important, quote unquote, because it's an invariant of the inviscid equations beside the energy. The history behind the fact that it was discovered so late is for another day. Okay, so what is helicity? It's a perfect example of an object which does not have helicity, because it's a vortex filament in 2D and the vorticity is perpendicular to it. So if you take two of them, you still don't have helicity. But if you link them, then there is helicity, because there is flux of one filament across the surface of the other filament. So in fact, Lord Kelvin played with knots, thinking that maybe they were the atoms of turbulence. Now, what is helicity? I think it is important to realize that you can define helicity in still an isotropic framework. That is to say, your correlation function are going to depend on the modulus of either the separation of or the wave number. Simply, you add a second function by saying that you are antisymmetric here. In other words, you are not mirror symmetric. So UE is going to be proportional to the energy, and UH to the total helicity in the fluid. Okay, so we have two determining functions for our correlation function in turbulence with helicity, and therefore a priori we have two scaling laws. But if you don't put rotation, if you do good old Navier-Stokes without rotation, it's a little boring. Now, helicity is being measured. Helicity has been viewed as possibly important in the atmosphere, simply because when helicity is maximal, then the Lamb vector, you cross omega, where omega is the vorticity, is zero. In other words, there is no nonlinear interaction except for pressure, for additional pressure. Now, that state, Olga has studied in the past, is not stable, neither I think it's attractive. So helicity is now measured in the atmosphere. For example, here, that's a rather recent observation of the planetary boundary layer during the day and at night. And I believe the three lines are the three components of the scalar product. And rather boringly, it's a Kolmogorov spectrum. Now, this was known for people doing numerical simulations in 3 dimensions, but of course not in that complexity and not at those Reynolds number. So helicity doesn't change the scaling as far as the spectrum is concerned, and helicity is shown here, a large-scale map for the US, or here, tropical cyclones with small shear or large shear. There is a correlation between shear in green and helicity in red. So it's being measured, and I won't talk about MHD on the sun, and there's plenty of helicity in that context.
It's zero sign, yeah? I mean, on the average, the sign is zero, close to it?
Doesn't matter. I don't know, but it depends. Still, you measure it.
So you plot the modulus of the spectrum?
Huh?
The modulus of the spectrum?
Yeah, yeah, absolutely. I don't remember how. They do talk about relative helicity, but you have to be a little careful in the literature for atmospheric turbulence. Relative is going to be relative wind, because there is a mean wind, and then you take the fluctuation, so you have to read correctly. So here's the relative helicity, which really is the alignment between the velocity and the vorticity. And in the small scales, even though globally the Taylor-Green flow, which is the French washing machine numerically, is non-helical, locally in the small scales, the vortex filament, this is a blow-up of the box, is either completely aligned or anti-aligned. And that's well known, that's been known for a long time. So helicity is measured in turbulent flows, but it does not alter scaling laws, at least at the second order level. And why? It's very simple to write that equation. It's that you write the equation for the density of helicity, pointwise. It is being advected, and then it's going to grow if there is an alignment between the vorticity and either shear or pressure gradient. So it grows locally, and that's been known for a long time, also in imaging.
Anik, and the viscosity term looks like that?
I think so. I mean, it's linear, right?
Yeah.
I'm writing an equations for v dot omega pointwise, and I'm going to have a linear term here. Okay, so now let's put rotation, solid body rotation, and therefore we have waves, and therefore we're going to look at turbulence with waves. So we can solve it, some people have done that, but is it useful? It's not completely evident. It's certainly useful to understand and think about the problem, but is it what we observe? That's another story. So we're going to have a phenomenology. I will not bother about the directions. You can extend it to the anisotropic case. And you say that there is a small parameter in the problem, which is the ratio of the wave time, here the initial wave time, 1 over omega, omega being the imposed rotation, and the eddy turnover time. And let's say that that time is small, then we expect the turbulence to be less efficient. In other words, we expect the transfer to small scales, the nonlinear transfer, to be slower. Therefore, we're going to say that the typical time of transfer to the small scales is divided by small epsilon. In other words, it's longer than the eddy turnover time. You do that, and you crank the phenomenology, which is now only dimensional analysis with that extra assumption. And what you find that if you impose a constant energy flux, constant with respect to wave number, you have a spectrum which is k minus 2, is in front a dependence on the rotation. When you turn the crank a little more, the structure functions are going to be p over 2, the exponents, as opposed to p over 3 for Kolmogorov. Okay, this is an old argument. Doesn't seem to be too bad. Let's look at the data. So the experiment, I must say the experimentalists have beaten us being the numerical people, show that as you increase the rotation in that direction, they look at the energy spectral index, and it's, okay, the error bars are big, but basically it's Kolmogorov 5/3, close enough. And then, when you go across this parameter, which is called the micro Rossby number, which is the RMS, vorticity, divided by the imposed rotation, when you cross that value, you have an increase of the spectral index that doesn't stop at k minus 2. I won't have time to go into this one, but anyway, it doesn't stop. Now, it's an experiment. It's not an easy experiment, and therefore there may be errors, or it may be a decay flow. I mean, there are reasons why we could explain the difference between the little phenomenology. So what does rotating turbulence look like? This is the vorticity here. Viewed on the side, the direction is, the rotation is in that direction, which is rather obvious, because you do see a trace of what would be called in the linear regime the Taylor columns, but you see that at small scales you have plenty of vorticity. This is a top view. You have plenty of vorticity in all directions, and the relative helicity is just the porridge, right? Plus and minus, very aligned at the small scales, but in all directions, because that flow globally is isotropic.
Why is it isotropic? Globally, I don't quite see. I mean, there's a strong rotation, right? So
right, so the large scales do see the strong rotation,
yes.
But here I am at small scale. So if I look at the, you're asking about my next slides, but if I look at my small parameter here, is the time associated with the wave, with the time associated with the eddy turnover time. So then exists a scale at which epsilon is 1. In this run, that scale is close to the dissipation scale, therefore to the cutoff. So there is some isotropy, in fact, in the small scales, but only very close to the dissipation.
I'm confused how you got the previous slide, because the previous slide is an experimental measurement of an exponent. But the exponent of what? The structure function or the correlation function would have strong contributions from non-isotropic sectors.
Right.
So why should I see K41 at all? If I measure just a correlation function, it should be a sum of exponents coming from the isotropic sector and the higher order sector.
Right, so I cannot answer for the experimentalists, although they are measuring anisotropic spectra. I will show you some a little later of spectra, anisotropic spectra for the numerics. Okay?
So we have to take that picture with a grain of salt somewhere.
Right. It's just a picture, because some people have an idea of rotating turbulence. The Rossby here was 0.3 for that image, but even if you go a factor 10 below, they think that it's waves. Not at all. It's very much like the usual turbulence, except that there is some order in the third direction. So we are looking at scaling of structure functions for rotating turbulence. This is the experiment of Bawood in 2002. This is the numerics in 2009. In both cases, this would be Kolmogorov 41 p over 3. Never do extended self-similarity when you have self-similar, because then you will find p over 3. It's very convincingly p over 2. And numerically as well, the only difference in the numerics is that it takes time to get there. This is as a function of time, and the flow evolves towards that flow. So there is an agreement between experiments and numerics. Now, if we take another forcing, which is not the Taylor-Green forcing, which is not helical globally, but the ABC forcing, which is a Beltrami flow, what happens? Well, things change. This is a cut in the box without helicity, the Taylor-Green. This is the vorticity. This is, the vertical component of the velocity. And this is a cut when there is helicity. The forcing is a Beltrami flow, and you have those very strong columns. So you know when you look at the flow that they are highly helical. So we know the flow looks different in the presence of helicity. That's the first remark. And when we look at scaling, so numerically it's a 1500 cube grid. Again, we look at the scaling of structure functions. Here's the p over 3 if there was no rotation. Here's the p over 2, which is the phenomenology I showed you, and the data I showed you before. And now we have approximately 0.7p. So we have two rotating turbulence flows, one with helicity, one without helicity, which are both self-similar, but with a different scaling. And this is beyond error bars.
Again, I'm a bit confused. So if you have the numerical simulation, you have all the data, so you can at your leisure project out on the irreducible representation of the symmetry group. So you get just isotropic sector scaling in one, just by averaging over the ball. Why did you do this? Then you see what are the various contributions to the anisotropy. This is sort of, this you get in every measurement a complete mass of contributions from isotropic and non-isotropic sectors. So I don't quite understand.
Right, but I'll show you.
So are these exponents or?
These are exponents of the structure functions.
Are they real exponents or a mixture of exponents that seem to be an exponent?
They are real exponents insofar as we measure them, and we can measure them in two ways. One is completely isotropic, or one is looking at the perpendicular plane. And there is not much difference because, in fact, the data is dominated by the perpendicular component, sufficiently that there is no mixture.
But what do you mean with the perpendicular component? In what direction is R?
Well, here we impose a direction, so it's R per.
Yeah.
Okay. So the horizontal. So it's very easy to take those differences in the plane.
Nick, when you take these exponents, it's you take limit r tends to 0, right? And you were mentioning the degree of anisotropy is different for different part. So
Okay,
does it
this
make
is done on a grid where we barely resolve the scale at which isotope is going to be recovered, and therefore your question does not really arise. We are actually measuring where rotation is strong, quote unquote strong, okay?
So you don't really take
We are not
R
looking at the
to the
isotropic
limit.
part here. We are not taking the limit R goes to 0. I have a dissipation scale, right? And the rotation is felt almost all the way to the dissipation. Not quite. When you look at the vorticity, you do see an effect, but almost.
But you must have two completely different length scales here.
Right.
In the vertical you have a, or in the vertical you have a much larger length scale due to the.
Not much.
Not much.
We'll see.
Okay.
For the next simulation, I will show you the ratio, and it's not much.
Okay.
In fact, the mixture of the small scales is efficient. So here's the experiment. They beat us. It's von Broekhoven in 2009. And what they find is that for their case, for that experiment, they find that they have structure function exponents that are aligned on 3p over 4, which is close to 0.75. So the only difference between the experiment and us, except that it's not the same technique, is that we attribute it to helicity. I do not think that they have that attribution yet, but they're aware of our work.
So is this a French washing machine on a rotating table? I mean, it comes from Gamma flow on a rotating table? Or what?
I do not know. This is the sketch of the experiment. So it's a small, I think it's about a meter, no, even 70 centimeters,
Yeah.
and they're turning this. This is not the French washing machine. Those people, they are in Eindhoven, I think.
They're what?
Eindhoven?
It's a rotating table.
Yeah, it's a rotating table, but I don't think it is mixed by two counter-rotating discs like
but
the
they do have
French.
helicity, you say. How do they get
No.
helicity?
I say they do not attribute it to helicity. They are not aware of whether, or they were not at the time,
Yes.
aware of whether helicity was a good separating
Right.
parameter. We attribute it to helicity. Okay, so why? Well, let's look at fluxes. So we are forcing it for this run. We are forcing at k equals 7, and you see the normalized helicity spectrum normalized by the forcing so that it dimensionally compares to an energy spectrum. And you can see that the helicity, or barely see, that the helicity flux is larger than the energy to the small scales, whereas there is no helicity flux, it's 0 to the large scales. But you know, there is an embryon of inverse cascade, but not much, because we wanted to resolve both ranges.
But
Okay.
what do you mean when you say it's larger? I mean, it's not the same dimension. They have
Yeah,
not the
yes.
same dimension.
Okay. I normalized by the forcing, and in those units, it is larger. Okay?
But is it mean helicity here? You have a mean helicity?
No, there is no mean
No,
helicity.
okay.
This is
So
the flux of
flux.
helicity, the nonlinear term for helicity, normalized by the forcing scale, because I need a scale. And that's a natural
Yeah,
scale, I
but
think, for
is
that
it a
problem.
flux of mean helicity?
There is no mean, there is
No,
no mean
okay.
flow.
No.
Okay?
No, but
It's a weak flux. It's a weak flux.
but what breaks the symmetry so you get
I am
mean-
forcing
Oh, you're
helicity.
forcing
Yeah,
helicity.
yeah, yeah.
Okay.
I am inputting. Now,
Yeah,
let me
okay.
remind you that full helicity Beltrami flow or zero helicity, that is to say at every point in space velocity and vorticity perpendicular, are perfectly unrealistic. In reality, if you take two vectors at random, they'll have some angle. So the realistic case would be to do the case in between 0 and 1, which we haven't done yet. Okay? So if you're not happy about those flux here, using a model, and I won't go into it, then you can have a constant flux in the two cascades. But that's a model, an LES, larger dissipation. Okay, so the message is energy flux to small scales is smaller than helicity flux. The small scale cascade is dominated by helicity. You don't see much, but this is the ratio, normalized ratio of helicity to the small scales to energy. This is 1 for no rotation, and it goes up with Rossby number, Not very much, mind you, but this is enough to make the difference in the dynamics. Here the value is like 5. And the Rossby numbers, in those cases, the smallest Rossby numbers are realistic for the atmosphere, but not maybe for some astrophysics. So what happens? You do a helical twist to the phenomenology. You do the same phenomenology as before, which is really wave turbulence, saying that the waves slow down the transfer to small scales, but the guy that's going to keep constant is the helicity flux. That's the only difference. Once you do that, dimensional analysis will lead to energy index, helicity index of the spectra, E plus H equal 4. Solution E equal H is 2, which is the preceding solution, but it could be different. So I'm going to look at the product of the energy and helicity spectra. This is why I'm showing you that. Just pure, simple dimensional analysis. Okay, but wave turbulence is going to end when the eddy ton over time finally gets small enough that it's going to win the battle. And at that scale, we propose to call that scale the Zeeman scale, which is the analog of the Osmidov scale for stratified flows. I wanted a name because when we are going to do both stratification and rotation, we'll need to distinguish between those two scales, a priori. Okay? But same thing, the definition of that scale is that the 2 times of the problem that I can think of, granted the Reynolds number is large, are equal. You end up with a scale that depends on rotation. So at a fixed Reynolds number, which say fixed epsilon, velocity of 1 length scale of 1, then as the rotation gets stronger, that scale gets smaller. So maybe sometimes you don't resolve it. And in particular, if you take infinite rotation, you will not resolve it. And I think that's part of the problem of the controversy with some people. So we are experimentalists, so we want to look at that problem. We are going to do a large run to resolve each range moderately. The inverse cascade range, because we think there is an interaction between the direct and inverse cascade, in the sense that the stronger the rotation, the more the energy goes to large scales, the less it goes to the small scales, so it affects the small scale dynamics as well. The wave modulated regime, the K minus 2 if you wish, then the presumably isotropic inertial range if it's there, and the dissipation range. So that's a costly proposition. Therefore, we did a computation on a grid of 3,000 cube points. 21 million hours, because they like to count that way, but on 30,000 processors, it's only 5 weeks. And if you consider that's about a quarter of the machine, it's like astrophysicists having 1 week of time on a big telescope. Right? That's about the order of magnitude of that computation. Okay, so here is the result. I look at the product of the energy and helicity spectra compensated by K4, and if the helical twist to the phenomenology of turbulence with waves is correct, it should be flat, and here it is. Not very convincing, because I want to resolve that part. So I didn't give too much room to this guy. This transition is obvious to the eye. It is also, if you just do, it's not here, but if you just do the dimensional analysis of what is epsilon and what is omega, that's exactly what you find. Around k equals 30. After k equals 40, this is the Zeeman, Osmidov, if you wish, scale. You have spectra which are very close to cosmograph. Their product is very close to k to the plus 10 third. Now, of course, forcing at k equals 4, there is very little inverse cascade, but there is some. Here we show, as a function of time, the energy in different modes. Those modes up here are at scales larger than the forcing, and there is growth with time. Those modes are scales smaller than the forcing, and have reached some equilibria, statistical equilibria. So we have, on the one hand, some inverse cascade, not much, and on the other hand, 2 cascades to the small scales, with a very clear transition. You know, you sweat when you send a 20 million hour run and you choose the parameters, you sweat. So anyway, we were completely wrong with the time step, so we couldn't run it as long as we wanted. So here are the angular variation of spectra, where theta is the angle between the imposed rotation in the z direction and the wave vector. And for theta equal 90 degrees, this is the solid line. As you can see, it dominates in the large scales. And that's why the question of whether we are looking at isotropic or an anisotropic spectra is relevant, but not completely correct. I mean, we are safe looking at the total one, at least up to here. This is, again, the phenomenological evaluation of the Zeeman scale. And there is a recovery of isotropy in the sense that all those guys collapse on this, okay? And here's the ratio of the perpendicular to parallel length scale, that is to say the, what is it called? The integral scale, but defined with the perpendicular or parallel spectra. This is the solid line. So it starts at very close to 1 and grows to 2. So it's not a very big difference. And on the other hand, it's the ratio of the 2D energy, that is to say the energy in the perpendicular plane, to the 3D energy. And it also grows. The ratio, the scales for the ratio of energies here. Now, a word about t equals 0. We in fact do a computation without rotation, or with in fact weak rotation, Rossby number of something like 10. Once that has reached a steady state, we say that's t equals 0 and we start the run with rotation. So it's a, we also have a study of high Reynolds number non-rotating turbulence. Okay? Remarkably so, maybe not, maybe it's obvious to you. When you look at the fluxes, this is the normalized helicity flux, this is the energy flux, and they are constant, going smoothly through that transitional wave number. So I have one cascade, in fact I have two as I showed you. And for those who are interested in relative helicity, which is the relative alignment between velocity and vorticity, it's very close to being completely aligned where I force at k equals 4, and then it drops on both sides. So we impose helicity at the forcing scale, but then the helicity decides to do what it has to do dynamically. Okay. And here are the angular spectra again. And what I want you to see is that in the large scales, that's wave number here, in the large scales you see that you have ellipses. That is to say you have a turbulence which is mostly 2D, whereas in the small scales it's much more noisy and it is circles. Remember, it's not very well resolved because we resolve several ranges. So the range where you want to look at that data is from 4 to 40, and then from 40 to the maximum wave number is 1000. This is a blow-up of the large scales. So I am about done. These are the structures. How do they look like? This is the run where the recovery of isotropy is very close to the dissipation length scale. You have that mess of vortex filaments, and you have those helical columns. This is the run where the length scale of recovery of isotropy is at k equal 30 or 40.
Sorry, what are you showing there in the bottom right?
Okay, this is a blow-up of this guy, and these guys are the vorticity.
It's the magnitude?
Yeah, magnitude, yeah. So you still see columns. You are in a rotating flow. You can guess the direction, right? But they're fuzzy because the small scales have recovered isotropy.
The red line is...
The red line is we injected particles. I may have put it here, well, yeah, anyway. And very close to each other. And this flow is laminar, so they go on, and you can predict. And then all of a sudden they're going to feel the vortex field, which is the random tangle of vortex filaments. So those columns, in ways that I do not understand, play a role in the intermittency, insofar as the self-similarity differs when I have those columns with helicity and when I don't. So we are presently computing the intermittency for those guys, but that's going to be very difficult. A, because we underestimated the, or we overestimated the computers at NCAR. They have a hard time handling 3,000 cube data. And B, because we have two ranges, so in each range we're going to have middle data. But it is being computed. Okay, so here's the summary. In the presence of helicity and rotation, the small scales are dominated by a helicity cascade. This provides a small quote unquote, but nevertheless, a small parameter for the problem besides the Rossby number, because the ratio of helicity to energy cascade to small scales, in which sense did I say, is large. I did not talk about the conformal invariance of the direct energy cascade, and I didn't talk about some limits that were, in fact, conjectured by Chakraborty, and we think that it's a good idea. That is to say, we are not going to go to be completely maximal helical, but we're going to be different. So that's, we think, is the limit of the energy spectra. I did talk a bit about that, and isotropy is recovered in the small scales. But, of course, there are questions. One, can helicity help interpreting laboratory experiments? I think that's a valid question, but Danton and others hate me, because it's not easy to measure helicity. What is the limit of the large Reynolds number at a fixed rotation? Now, at a fixed rotation, the range in which rotation matters is not very large, and the range in which I have recovered Kolmogorov is very large as my Reynolds number. And therefore, am I talking about an empty set? Interesting.
Yeah, but since we don't know what's happening at each Reynolds number, even without rotation, well.
Okay. Now, what about the intermediate case, when I'm not fully helical or fully non-helical? What happens? I don't know. Cambon says that then in the anisotropic case, when you write the correlation function, there are other terms, which he calls polarization anisotropy. Here there's zero. Does it matter? Does it play a role? I don't know. And those computations are, shall we say, heavy. So is a direct energy cascade different when there is no helicity and full helicity? We already know that they are, but in the intermediate case, I don't know. So Pablo and I make different bets. Pablo is bold, so he says, no problems. As long as you have a little helicity, you're okay. I am prudent and say, I want the data. Okay. Does the kind of imposed forcing play a role in the dynamics? And the answer is yes, because if it is helical or non-helical, we already know that it does. But another guy could be random versus deterministic. We've taken very simple flows that at every time step we inject, and 2D versus 3D.
I mean, if you have anything like an inverse cascade without forcing, you'll be in trouble.
Right.
Yeah.
Not completely right. We can discuss that. Pablo proved me wrong. I said the decay case and the force case, they're equivalent, some ergodic theorem. But in the case of an inverse cascade, where does the energy come from? And therefore there is no inverse cascade in the decay case. Well, Pablo proved me wrong. He did 50 runs, 2,000 square resolution, and he did an ensemble average and time average. And you see a trace of a -5/3 inverse cascade in that case, in the decay case.
Yeah, but transient.
Oh yes, of course.
The decay is not transient.
Yeah, it is a transient, but nevertheless,
all right.
it is, and it is important.
That would rule it out.
It is important for the experiments, because some people see a -5/3, some people interpret it as an inverse cascade, some people say, no, it is not. So this point, I mean, I'm very glad we have that numeric. I'm not glad to be wrong, but okay, what happens locally in space? Is there universality? I mean, we have two experiments and we have two numerical experiments that show clearly distinguishable slopes for the self-similarity. And how are we going to model? Because if we recover isotropy in the small scales, we don't need an anisotropic model. Is that true? And how can we verify it and measure these models? And that's it. If you want the code and if you want the data, please ask me. We are old-fashioned, just send me an email.
I'm still confused between the difference between existence of helicity and anisotropy. So can you clarify? So I have a couple of questions. Can you have helicity in a purely isotropic situation?
Yes.
Yes. I thought
And that's
so.
a matter of definition.
Well, yeah, I thought so. But then we don't accept scaling. We accept a mixture of two things. Maybe with crossover. So you can have, if one flux is dominant at some range of scales, you get one scaling. If the other flux is dominant at another range of scale, then you have sort of a crossover between two scales. So that has nothing to do with anisotropy.
Correct.
Okay, so then what we saw in your changes of exponents, why do you interpret this as return to isotropy? I thought it's just question of which flux is dominant in those cases. It's nothing to do with anisotropy.
I love to say that, I think you're wrong.
Okay? I asked, I didn't say it. Okay?
There is a paper by Suzanne Curien where she says, without rotation, that there may be a transition where in the small scales you have a different regime than in the large scales. I am not sure she's right, but it's very difficult to actually measure. So let's forget that and let's go with rotation. In the presence of rotation, the run I don't have to prove you wrong is the same run as here, but with the Taylor reinforcing, but there is no helicity, at least globally. Okay? So I don't know. For the moment, I am conjecturing, for reasons that would take time to explain, but we can discuss them if you want, that I think that in the globally non-helical case, I am going to have the same transition, which is due to the waves not being as important in the small scales, because their time is just now too large compared to the editor.
So I didn't quite understand. So how is this related to anisotropy? So why this transition you assign to?
Because I think the logic here is that in the presence of rotation, I have anisotropy.
Okay.
But if the rotation becomes weaker for some reason, that is to say, I look at the local Rossby number, then in that case, rotation doesn't matter any longer. I am back to isotropy.
Okay, so in this case, if you took the data at any length scale and just projected it onto the isotropic sector by averaging over a ball, then you should see one spectrum all along, one exponent, right? Just the isotropic sector. I'm trying to separate between helicity and isotropy. And I think you can do it if you want to see, okay?
I think I understand
and you have
what
the
you're
whole data,
saying.
so it's easy to do.
I think I understand what you're saying, which is you want to see the spectrum of the isotropic sector
Exactly, and then
flowing smoothly.
exactly.
And in the large case, it's dominated
Right.
by the other guys.
Right.
No, that we can do that.
Yeah,
yes.
easy.
But I mean, in the experiment.
I mean, I would expect you would see some crossover in the non-rotating case easily if you had fractional helicity, because then the helicity will only attain the 5/3 spectrum at high wave numbers. Now it will start doing that already at the 100 proportion scale.
I am not sure this is correct.
No?
We see the data for the atmosphere, and you asked the question how much fractional helicity we have in the but in the atmosphere it seems to be that the helicity has a 5/3 spectrum. So I do not think, I mean, I know you have MHD and the dynamos in mind, but and fractional helicity plays an immense role in MHD. But here, I don't think so, for the very simple reason that A, I think I have Kolmogorov spectrum for both helicity and energy, and B, I think that with or without helicity, without rotation, I have the small scales highly helical. The vortex filaments are highly helical. And that's why they live long. Yo-yo.
I'm thinking about I'm trying to reconcile it.
Happy birthday. Good. That's good.
Do you have a comment?
No, I have a very simple question. That you're forcing mean helicity in your simulations, but you're comparing with the experiments, and you say we have the same kind of results here. We interpret it as being due to the helicity, but in the experiment, I suppose you don't have mean helicity.
Oh, I bet you have helicity.
Yeah, but
No,
mean
what-
helicity. What breaks the symmetry in the experiment? So you actually produce
If you
either
force-
positive or negative mean helicity.
But if you force a flow, why would you, naturally, why would you force with u and omega perpendicular to the point?
No, you
on,
force it.
on average, you're
Yeah.
going to have some helicity in your forcing, be it numerical, where I control it, or not.
What mechanism would break the symmetry?
I mean, if you have some sort of stochastic forcing and you take a big enough thing, mean will be zero.
Yeah,
Unless you do something to make the mean non-zero,
yeah.
which is what you're doing
Yeah,
with
if
your
you
special
take,
force.
if you take a random forcing, I can stipulate the helicity of that flow by correlating u and omega.
No, but sure, but I'm saying you'll get a very broad distribution which will be peaked at zero.
So you're asking.
But in the experiment,
question-
what mechanism breaks the symmetry in the experiment? So you get, if you imagine an idealized experiment, you either want to produce helicity or you don't want to.
Well, look at
So how mean?
this is -1, this is +1, this is 0. And you say that by picking at random, you're always going to find 0. I disagree. You're going to have helicity in an experiment.
No, in any experiment, but I'm saying then you average long enough or over enough forcing, that will give you.
Or you
Okay.
experiment.
That is a different question. You're asking a question about long time averaging.
Yes.
And we know that there are reversals, and we know that there are states that are attractive, and then it's going to balance to another state. Agree with that.
Okay.
There is no continuous force in an experiment, right? So it's just the grid passing through rotating fluid.
That depends. You do have false turbulence, everything.
Noisy experiment.
Okay, I said, we have here a coincidence. We have two experiments. We have two numerical experiments. And in both cases, experiments and numerics, we find two power laws. I say that from a numerical point of view, it's the helicity that's the determining factor. I say that in a realistic flow, there is helicity, it's measured in the atmosphere. Where does it come from? Well, there is rotation.
But did you do the simulation without the helicity?
Yeah.
Yeah. And you got something different?
I got two different power law for the self-similarity of the structure functions, with and without helicity. Okay? And if there were not the experiments, you would not believe me. Thank God there are the experiments.
Okay, perhaps on that note, we should break for lunch.